In this next lecture, we're going to talk about algebra with functions and composition of functions. So we want to be able to combine functions to make new functions and evaluate those functions, which is quite common in mathematics. So let's say that we have these two functions here. F of x is 4x minus 3, and g of x is 2x plus 5. So let's write a formula for each of the following functions. So we're going to build these new functions using f and g. So one way to do this is to add functions. And the way to do that is so the function is f plus g, and we'd evaluate that at x, but the translation of this is actually just to do the following. All you're going to do is take f of x and add it to g of x. So this is actually the definition of the sum of f and g. You would just add the two functions. So we will just do that. So we will add f, 4x minus 3, and we'll add that to g here, 2x plus 5. Okay, so then we can simplify, combining like terms. So the 4x and the 2x combine to give us 6x, and then these two will combine to give us plus 2. Okay, subtraction is very similar. So this f minus g, that's a function. Evaluated at x, all you have to do is just subtract the two functions. So the definition is actually f of x minus g of x. So you see that the way that this is defined is you're saying f minus g evaluated at x, and that translates to evaluate f at x and then subtract the evaluation g at x. So let's just subtract those. Now here we have to be a little bit more careful because we're doing a subtraction. So it's a good habit to write, whenever you have to do the subtraction, write the thing in parentheses, because you're going to have to distribute that minus, as we've seen in many problems before. So this is actually 4x minus 3 minus 2x minus 5. So the 4x minus the 2x gives us 2x, and the minus 3 minus 5 gives us minus 8. Okay, now in this next one, we're going to look at g plus f of x. So the translation of this, by definition, would be g of x plus f of x. However, addition is a commutative operation, so it's going to end up giving us the same answer up here, but let's just see that. So g of x is 2x plus 5, and f of x is 4x minus 3. And again, we can combine like terms. The 2x and the 4x gives us 6x, and the 5 minus the 3 gives us plus 2. So indeed, we did get the same answer as we had up here. But it's good to see, how these things translate and to get used to this. Okay, so the next example here is f times g. So make sure you realize this. In this section, we're going to have another notation that kind of looks like a multiplication, but it's not. That will be composition. But here, if you just have a dot, just a plain dot, that'll mean always just plain ordinary multiplication. So how do we find this function? So f times g evaluated at x. Well, all you have to do is just multiply f of x and g of x. So what will that look like? Well, f is 4x minus 3. We're going to have to write that in parentheses, and then we will multiply g. And if you remember from the last lecture, we had several ways that we could simplify this. Okay, so one way is you could use the distributive property, right? I could distribute this whole factor into these two terms. And another way that we're going to use quite frequently is we're going to use this FOIL method, but it really doesn't matter as long as you get to the same answer. So if I distribute this, then I have 2x times this whole factor, 4x minus 3, and then plus 5, the 5 here, times this whole factor again, so 4x minus 3. And then we will distribute these in. So the 2x gets distributed in. And what will we get? So 2 times 4 is 8, but then the x is multiplied, so we actually have 8x squared. And then the minus 3 and the 2x give us minus 6x. And then the 5 gets distributed, so we'll get plus 20x. And then minus 15. And then we can simplify a little bit more, so 8x squared. plus 14x minus 15. Okay, well, what about doing a division? So this is fine as long as the g of x is not equal to 0. So the translation is just going to be f of x divided by g of x. But as you simplify this, if g of x were to be 0, that's not allowed. So yeah. So you're allowed to do this as long as g of x is not 0. So what was f? Well, f was 4x minus 3. 4x minus 3. And g was the 2x plus 5. Okay, and that is as good as it gets, pretty much. This is an example of what's called a rational function. But yeah, there's no further simplification that we could do. I mean, you could break this up into two fractions, but that doesn't really make it any simpler. Now, note g of x itself is not equal to 0, but there are x values that make that denominator equal to 0. And so if you were to consider the domain of this function, we would not allow that x value. And I'll have you think about what value would that be? Okay, so moving on, how would we simplify this? So f times f, that translates to f of x times f of x. And f of x was the 4x minus 3. So that's 4x minus 3 times 4x minus 3. And so we could simplify this the way that we did up here, or we could use kind of this FOIL method that I was talking about before. So how does that work? So you do the first two terms multiply to give us what? So that'll be 16x squared. The outside terms, so 4x and the minus 3. So what would that be? Minus 12x. And then the inside, so let me switch to a different color so this is a little bit clear. So now do the minus 3. So the minus 3 and the 4x gives us another minus 12x. And the last two terms is minus 3, which will be positive 9. But then we can simplify this, combine like terms, and we'll get our answer. So the only thing that we can really combine here is the minus 12x's. So we'll actually have 16x squared minus 24x plus 9. Okay. So another type of operation that we can do is what's called composition, and we actually have seen an example where you do this, but this is a special kind of function. Okay, so this is it's not like the four basic operations: addition, subtraction, multiplication, division. Composition of functions is another way of combining functions together. So what does this translate to? So whenever you see this notation, which is an open circle, that's not a multiplication. This denotes the composition. Okay, so that notation right there, that is composition. Okay, now the direct translation of this is you're going to have f of g of 0. Okay, so the number 0. Okay, so let me write that up here. So what does composition actually translate to? So if you ever see f compose g of a some input, right? So let's say that it's x, for example, then that translates to f of g of x. Okay, so it's just a way of sort of having an outside and an inside function. And with that, you can build many, many different types of complex functions. Okay, so that's exactly how it translates to. So see that it's not actually doing an operation like multiplication, division, addition, or subtraction. It's combining them. So it's composing the functions. That's the way that the terminology works. So here, f compose g and then evaluate it at 0, well, that'll be f. That's the outside one goes on the left, the inside one goes on the right. So f of g of the input, 0. Okay, so if you happen to have an actual value you're composing, let's say that it's a, it's the same thing, it's just evaluated at a, which is the situation that we have here. So we're evaluating at 0. So how do you proceed with this? Well, we're going to figure out what is that inside value. So f of, and now you have to look at what is the g function. G is x cubed minus 1. So we're just going to take our 0 and plug it in here. And so we'll have 0 cubed minus 1. So that'll give us minus 1. And see, we're just carrying along f. We haven't evaluated that yet. And then you will evaluate this at negative 1. So now that'll be 3 minus negative 1. So that'll be 3 plus 1, which is actually 4. Okay, now there actually is another way to do that simplification, but let me just stick with this procedure because I think that's probably the easier method to follow, and then I'll show you the alternative. I did do this actually in a previous example, but it's good to keep seeing things over and over again. You know, the repetition really helps. It's like practice, right? Okay, so G compose F evaluated at 0. Now, you know how above we saw that addition was commutative. You know, multiplication is generally commutative as well. But composition, we're going to see, well, is this commutative? Well, let's see what happens. So G compose F of 0. So first, let's figure out what is f of 0. So carry the g along. So f at 0, we're going to plug in 0 for f, which will be 3 minus 0. So that simplify the inside, which is just g of 3. And then now take this input and plug it in for g. So we have 3 cubed minus 1. So this is 27 minus 1, which is 26. Okay, and note that these two values are not the same. So that's quite interesting because this example shows you that these two functions do not agree. So you can't just swap, you know, which one's the outside and which one's the inside. That's going to affect the outcome. All right, so order is very, very important when you're talking about compositions. Okay. All right, now let's write out what these functions actually are for a general x instead of just these zeros. Okay, so once we actually solve this 3 here, you could plug in 0 and see if it matches that output of 4. All right, so what is f compose g? So that would be f of g of x. Okay, so what is g of x? Well, g of x is right here. That's x cubed minus 1. Okay, and now that is our input. Okay, so all we got to do is just take this input and replace wherever you see our input. So you know how f is, you take your input and you're just going to do 3 minus that input. Okay, so here's our input, x cubed minus 1. So all we got to do is it'll be 3 minus our input. Okay, so that'll be 3 minus x cubed minus 1. All right, and then simplify if possible, which it is. So distributing that minus, this will become a plus 1. So then we actually get 4 minus x cubed. Okay, and you can check yourself real quick with this first one that we did. If you were to plug in 0, what would we get over here? Well, if I plug in 0, then I'll get 4 minus 0, which is 4. And that matches our answer up here. All right. So continuing, let's see what g compose f looks like. So g of f of x. Okay, so here let's replace the input. What's f of x? That's 3 minus x. So we'll have g of 3 minus x. Okay, and now 3 minus x is our input for g. So you come up here, and the input, what do we do with that? Well, we cube it, and then we subtract 1. So this would be 3 minus x cubed minus 1. Okay, and this is an acceptable answer. You could expand this, okay, but maybe do that only if I specifically ask you to. because expanding that, you're going to have to do, it's going to be more work than the foiling that we did up above. But yeah. So in this third example here, we have two functions. F of x is x over 6 minus 2, and g of x is 6x plus 12. And so we're told to show that this is true. Okay, this expression here. So we want to show that f compose g of x is the same as g compose f of x, and it turns out that that's x. So what we'll just do is we'll actually just simplify this into two steps. So let's first figure out what is f compose g of x. Okay, we'll simplify that, and hopefully we'll get x. And then we'll do the same thing for g compose f of x and see if we get the same thing. So what is f of g of x? Well, following the same procedure that we had up above, this will be f of g of x. And we know that g here is what? So now this will actually just be f of, and let's replace g of x with what it is. So that'll be 6x plus 12. And that's now going to be our input for f. So now let's just take our 6x plus 12, and that's going to be our input. Okay, so x is our input here, and that gives us just x. But now our input is actually 6x plus 12. So let's replace wherever we see an x with 6x plus 12. Okay, and can we simplify this a little bit more? Well, yes, I could divide both of these, right? This is 6x over 6 plus 12 over 6 minus 2. That's how we can separate. You know, you can separate a fraction like that always. You know, a plus b over c, you can always write that as a over c plus b over c. Okay, you cannot do this though. This is a very common mistake. Okay, you cannot break this up. Okay, so this is a big no-no. You can't break up a over b plus a over c. Okay, you can't break it up like that, but you can definitely break up an addition in the numerator over this common denominator. Okay, but this is a big no-no. That's a very common mistake throughout algebra, pre-calculus, calculus. I see people make this mistake all the time. So get into the habit of not doing that early. Okay, so this is just reduces to x plus 2 minus 2, which is just x. Okay, so we got that this first part is definitely x. Okay, but what about the second part? So let's see what that is. So g compose f of x. So what do we get? So this will be, all right, so well, by definition, this is g of f of x. Okay, now what is f? So f is right here. So this is x over 6 minus 2, right? And then now that is going to be our input. So over here, our input for g is x, and there's only one place that we put the x right there. There may be many places that you have to put the x, okay? But right now, there's just one place. So we'll do 6 times the input, x over 6 minus 2, and we have to add 12. Okay, so now let's simplify this. So distributing in the 6, we get 6x over 6 minus 12 plus 12. So the 12's cancel and the 6 is reduced, and so we get x. So indeed, these are all equal, right? So together, so this is true, right? This is also equal to x, so all three of those are equal, right? So f compose g of x is definitely equal to x, but that's also equal to this guy, g compose f of x. Okay, so all three of them are equal. Cool. This is a very important situation, and we'll discuss this a little bit more. But this type of thing is quite important, and we will see it again.